In a world now increasingly adopting AI, this entire project was done with absolutely no AI, and accomplished entirely with the skills, tools, and equipment I have acquired over decades. You'll want to hang around to see the entire process. Unlike others who have some sort of prestigious design degree and can beautifully hand sketch their concepts, my ideas rarely take shape on paper or even outside my mind until I reach SOLIDWORKS and directly start sketching and 3D modeling the shapes in CAD form. Occasionally, I'll have a rough napkin sketch, but for the most part, it goes directly into a CAD sketch and model from my mind alone. From there, I'll usually 3D print the pieces to have the idea in my hand, see how it works, how I like it, see if it needs any adjustments or changes, and then I head out to my shop. To start off in the shop, I turn on the air compressor, and then the lathe, and then the mill. And most importantly, I let in the fresh air and natural light, which may or may not include bugs and, on the rare occasion, a bird. Most of the tools I need for this project are already loaded in the machine, but I do need to get a couple more. For most new projects like this, I usually need to load a few tools, if not many. Here I'll grab a few collets and tool holders as well. Because of titanium's difficult machinability, I try to use some of the best tools engineered for cutting it. Here I'm loading some of those tools into the tool holders and setting a rough gauge length on them. Then fully tighten them into the ER16 collet chuck. The hangout distance on these tools is a little bit longer than I normally like, and that is why I'm measuring for an appropriate gauge length to reduce vibration in cutting, otherwise known as chatter. Next, I load the tools into the spindle and touch them off on the presetter, and then record that tool's Z-height location. A part of the process that I missed recording takes this raw material and this dovetail cutter and cuts these dovetail features, which interfaces with this dovetail fixture vise for use in the fourth axis. Once it's tightened into the fixture, I use the edge finder to locate the X and the Y axes, and enter the location in the offsets page. Then I check for flatness and the Z height, and enter the Z offset. At this point, I've already loaded the program, so I'm ready to hit go and let it eat. After about an hour of roughing and finishing all of the features, the first half is done and it's ready to come out. Now, due to the complex lofted features that give this part its shape, there aren't many flat parts to hold onto it with, and it ended up tapered in a way that makes it kind of difficult to hold, sort of like trying to pinch a watermelon seed. That serves to be a bit of a challenge to work around with traditional work holding methods that are most commonly used in CNC millwork, where 2D shapes, like from these parts I made for a past project, can have aluminum soft jaws for a vise, machined to match their contours, and they can easily hold the parts for additional machining operations. So with these limitations in mind, I decided to borrow an unconventional work holding method from the aerospace industry, where they often have to hold on to very challenging thin-walled parts like jet fan blades and impellers. For this, I needed to design and make a custom fixture to hold the parts using liquid bismuth tin alloy. But I created another problem for myself here. In the overall design, I included 2 alignment pins for each part to central node interface. This meant the pins would either need to be permanently press fit into either the node or the fins. Since the face of the fin part that would receive the 2 holes in it was not parallel to another flat face on the other side, using the Schmidt arbor press to install the pins into that wouldn't really be easy, or even really possible without some sort of additional fixture. And no real benefit to this option existed. So instead, I opted to install the pins into the central node because of its always opposing parallel sides to easily aid in installing the pins. The pinholes would also serve to time or orient the position of the fin parts in the second op bismuth fixture, which consequently also needed pins pressed into it. So if you follow me here, I went to drill and ream for press fit pinholes into the central node and the fixture, but slip fit pinholes into the part. But in the haste of using this method, which I have used so many times before, I mistakenly drilled and reamed the holes in the fin part to a hole size with too big of a slip fit tolerance, only thinking of their need to clear over the pins installed into the node. However, that same hole size tolerance is looser or more open than what is needed to accurately locate the part in the second op fixture. And so I realized, to my horror, that the part installed onto the pins in the fixture I had spent all day making was loose and provided about a 12 thousandths of an inch rotation on the outside edges of the part in the fixture. This was no good. I needed to maintain less than 5/10,000ths of an inch, which is about 24 times more accurate, or better, in the alignment of that part. I was at a loss on what to do, but needed to figure something out. A divine thought occurred to me that I still had enough real estate in the fin part to re-drill and ream a second set of press fit holes, just a few degrees from the current holes in the part and fixture, and then lathe turn some new pins for the fixture to clear those new press fit holes in the part. This is why there are 4 pins in the fixture, 4 holes in the part, and only 2 pins in the node. Crisis averted, and I was able to carry on after a bit of brainstorming and talking myself off of a metaphorical ledge. With that all sorted, the fixture I made is then loaded into the machine and located using a dial test indicator for position. Then the position is set in the controller, and I can remove the fixture to more easily load the part and add the 4 walls at the bench. Then the part is carefully loaded onto the 4mm cylindrical boss of the fixture and clocked into the proper position using its 4 1mm locating pins. Next, the 4 aluminum walls are added to create a cavity for the liquid bismuth to set up in. The assembled bismuth fixture and part are loaded back into the vise against the part stop, tightened, and then torqued down to spec for repeatability. To prevent any chance of the part moving in the liquid bismuth, I add a C-clamp that I made to secure it. In this next step, I preheat the fixture and part to prevent any thermal shock that would arise from adding 300-degree liquid bismuth to ambient temperature titanium, steel, and aluminum, which can cause dangerous spatter and splashing of molten metal. I simply melt the solid bismuth used on the last part back down in a thrift store pot on a single burner to use on the next part to be made. Because I use this method on a lot of prototype work and other difficult to hold organic shaped parts, I've learned this process can add a lot of time to the overall machining project, depending on how much thermal mass there is in the size of the parts and fixture, as well as the required amount of bismuth. Aside from just waiting for it to cool and harden, I've tried different ways to speed things up when I have more of a timeline to work on. One that seems to balance the time and be the most thermally stable is this Venturi cold air gun that I have. Don't ask me how effective it is against waiting, because, honestly, I haven't timed it. I guess I mostly just want an excuse to play with the Venturi effect. And obviously I removed the clamp before I hit go on the next part. With the part fully enclosed in bismuth, I can now machine out the internal features of the part. It may look like it goes quickly, but it actually takes the longest of any of the machining operations of this whole project. And to make 2 assemblies, I had 24 of them to make, each with this setup. This part is done, and I can easily remove it from the bismuth fixture after taking the 4 walls off. In most cases where I use this method, the parts are so well secured that I usually have to melt the bismuth back down and extract the parts when they float to the top of the molten bismuth. But in this case, the tapered shape helps it pop out with a little physical persuasion. Once all of those pieces have been completed, I can move on to setting up the next part of the project in the 4th axis on the mill. This part serves as the central hub for all of the other parts and has 18 facets, 12 of which need to be machined on individually, so the rotary axis helps reach at least 4 of those 12 faces that need to have holes put in them in one setup. If I had a 5-axis, I could reach all of those faces except for the bottom face in just one setup. Here I have to pause after the thread mill machines the threads to check for proper fit using a screw that I have. Then I finish the rest of the machining operations and cut down to a tab that can easily be snapped off. So without a 5th axis, after machining as much as I can in the 4th axis, I take it to the vise to finish the face where the tab was, and then add the holes to the remaining 8 faces. I only had to make 2 parts, but I made a third as a spare, just in case I messed up along the way somewhere and needed an extra one. Even though that's only a few tools for drilling, reaming, and threading operations, you can see that there's a lot of interaction with the machine to get through all of those holes. Now you can see the beauty of having a 5th axis in that I could have done all of this in basically 2 setups instead of like 14. It's a tool limitation that I have to design and work around, but I try not to let it stop me, and it's forced me to be pretty creative about how I use a 3 and a 4-axis setup. With the machining finished on those parts, I can move on to making the screws. Using my 2D drawings from SOLIDWORKS, I plot out the points and hand program the G-code for the CNC lathe. This may seem old school, but you'd be surprised how many screw machine shops and turning shops still mainly hand program their machines today. Here I load the 1/4-inch diameter titanium bar stock into the collet for the turning operations. You'll have to pardon the coolant for the clarity here. It makes it kind of difficult to see in the roughing of the shape. It sure makes it fun for proofing out the initial program and setup too. Here I can test the thread fit with the mating part, the hub. Now I clear out the corner radius from the finish tool and part off the screw. Dig it out of the part off tray and clean it off. And prep it for heat coloring with the butane torch. I'm going for a nice gradient of bronze, purple, and blues, and this has to be applied very carefully. After it's cooled off, I load it into my watchmaker's collet block to finish the head back in the CNC mill. I rarely need to run both machines at the same time, but this gave me an opportunity to do just that. I actually made 2 versions of this screw, one where I heat colored the head prior to finishing it, where the millwork provides a bit of a contrasting highlight to the proprietary drive geometry, which you can see here, and one where I heat colored it after the machining was complete. In this process, I couldn't make up my mind which I liked better for the end result, but because I was only making 2 sculptures, and I decided I liked both screw finishes equally, I could apply one set of screws to each version of the sculpture, making each piece technically unique. Because there aren't many good off-the-shelf titanium screws, I chose to make my own custom ones, but that meant I also needed to design a custom screwdriver as well. So I cut off a few brass and aluminum blank pieces on the lathe to load into my collet block to make a few custom hex to quad drive screwdriver attachments for my trusty Vera nut drivers you can see right above my hands on the bench there. Then it goes back in the mill to cut the female side of the driver. This required some very small, extended reach tools to cut the internal quad drive feature. Like this 1/4 inch long by 1/2 millimeter diameter carbide end mill running at 30,000 RPM to clean out all of the corner radii. Then I take it out and flip the part over to machine the male hex drive side of the screwdriver attachment. You may be wondering why I chose aluminum and brass instead of, say, steel for a screwdriver material when they're both relatively soft metals. But what you should also know is that titanium, while extraordinarily tough, lightweight, and strong, is still somewhat soft and scratches quite easily. Because of that, I wanted to use the softest but strongest materials I could use for a screwdriver, to avoid risking scratching the finishes on the screws. The 5mm hex of my screwdriver attachment interfaces perfectly with a Vera nut driver. Which then fits my custom screws perfectly too. With all the parts machined now, I move on to cleaning them in an ultrasonic cleaner in preparation for assembly. I load these parts onto some titanium wire because the central nodes are also going to be colored blue, but instead of using the torch here, I'm going to use electrolytic anodization, which is more repeatably uniform in color and reliability. The setup involves a cathode in an electrolyte bath, a constant voltage source, and the titanium parts serve as an anode. Voltage is applied. In this case, I use 24 volts for blue, and a thin titanium dioxide layer is formed, reflecting blue light. Next, they go to the fiber laser for some markings. Now, a series of very tight tolerance stainless steel pins are interference press fit into the node for aligning the fin-shaped parts. "24 pins go into each node, and now I have a part that resembles a naval mine that would be a formidable opponent to bare feet if I left it on the carpet for some dumb reason. It is now time for the final assembly, where each fin is carefully aligned and secured to the central node with its mating screw, with the help of the custom screwdriver I made. And there it is, all assembled. 12 titanium fins, 12 titanium screws, 1 titanium hub, 24 stainless steel pins. Each is serial numbered out of 2, and only one piece will be offered for private collection. If you enjoyed this video, please like, leave a comment, subscribe for more, and share with someone who might want to see it. Thanks for watching.